the next speaker is Sarah Loos, and I cannot read your title, so I keep my full screen, who's going to talk about the role of non-conservative interaction in non-equilibrium systems. So the floor is yours.
Thank you very much. First I want to thank the organizers for inviting me and giving me the opportunity to speak at this very nice workshop. It's a great pleasure and honor for me. The work that I'm presenting was mostly done at ICTP, where I'm currently a postdoc, but this is actually my last day at ICTP. And some of it was also done at Leipzig University and Technical University of Berlin, where I was postdoc before coming to ICTP. And this is some of the co-authors and collaborators on this work. So I'm going to discuss about the role of non-conservative interactions in non-equilibrium systems. And I want to start with setting the broader and more general scope of the topic. So a common frontier in soft matter, statistical physics, and so on, is to find a theory, or I should say theories, for non-equilibrium systems. And in order to do so, we must understand what are the fundamental principles and universal mechanism that govern such non-equilibrium systems. And the framework of stochastic thermodynamics has proven to be very valuable. Indeed, many of the laws found in stochastic thermodynamics apply far from equilibrium. And in recent years, there's a lot of attention on the entry production rate defined as this logarithm of the path probabilities. And this definition is also applied to systems that are a bit farther away from the field of the original idea of stochastic thermodynamics. So, for example, to complex biological systems, such as these hair bundle cells here, cellular sensors, or even the movement of bacteria or fish. And now it's also generalized to field theories and measured in biology. And I want to stress something that I guess in this audience everybody is aware of, but it still is important to keep that in mind, that if we apply these kind of quantities and laws to this system, we have to acknowledge that we consider mesoscale coarse-grained models, and all the variables that we look at are effective variables. And often the connection to first principles is elusive or might be lost completely. And if you, for example, think about a robot or something. And what I want to discuss today is the emergence of non-conservative interactions. So what is a non-conservative interaction? Well, in general, there's any kind of interaction that cannot be represented by an interaction Hamiltonian. As an example, look at these two fish here within a school of fish. The red fish will react to the blue fish, but not vice versa, because this interaction is mediated by visual perception. And there's no reason why this should be conservative. In fact, it's most likely non-conservative, and in this case, non-reciprocal. And in non-reciprocal just means that it violates Newton's third law. So actio equals reactio is violated here. If I sum up the force that the interaction force applied on both particles, they will not sum to zero. Also, if I'm staying with this example, the interaction between two fish would not be instantaneous, but it would be time delayed. And this is simply because of the fact that there's a finite time for the signal to travel and a finite information processing time, giving rise to time-delayed interactions, which is another type of non-conservative interactions. And in addition to these macroscopic examples, I could now give you a long list of mesoscale or microscale examples how non-conservative interactions emerge, such as, for example, flows in the surrounding fluid, or if some underlying chemical reactions have been coarse-grained. Hydrodynamics can give rise to non-conservative effective interactions. Or if I think about bacteria, of course, also chemotaxis or any kind of cognitive agents that are present can give rise to delayed or non-reciprocal interactions. And in general, one can say that any kind of interaction that is mediated by a non-equilibrium medium should rather be expected to be non-conservative than conservative. And we want to understand what are the thermodynamic implications of having such non-conservative interactions in a model. And before I do so, I want to motivate it a little bit more, because I think non-conservative interactions represent an interesting class of non-equilibrium systems. So I just want to give you this perspective. So first of all, traditionally in statistical physics and thermodynamics, people have studied passive matter. And passive matter can be brought out of equilibrium by injecting energy, usually via the system boundaries or just from the initial conditions. So if I have a block of ice, I can bring this out of equilibrium by heating it up. In recent years, the attention was more put onto non-equilibrium systems, which are intrinsically non-equilibrium. And here, an important class of systems is active matter, where the energy injection is on the level of individual particle trajectories. And this, as an example, you can think of the bacterium, where the self-propulsion is, of course, correlated with the particle orientation. And this is a type of driving which is directly on the level of the stochastic particle dynamics. And if you like, systems with non-conservative interactions can be considered as a higher order active matter system. So here the energy input comes on the level of particle pairs. So it's not only correlated with the stochastic dynamics of one particle, but with the pair dynamics. So this kind of driving comes, so to say, on the level of the two-body dynamics, which means on the level of the structures that are forming. And I just think this is an interesting perspective and motivates, for me, why we should put some attention onto this. And indeed, non-reciprocal interactions are currently a kind of hot topic in the study of many-body dynamics. There's lots of high-impact papers published on this topic. But of course, I want to stress that in the community of stochastic thermodynamics, non-conservative interactions have also been considered by many authors. So in many, many models that you know, there are already non-conservative interactions. I'm sure everybody has looked at them. Here, I just want to put the focus onto them and and consider them from a different perspective, so to say. So in order to understand what is the impact of non-reciprocal coupling, we consider the most simple example system here, linearly coupled degrees of freedom by Langevin-like models. I have n degrees of freedom, and the non-reciprocity here comes simply in the form of an asymmetric coupling matrix. And special cases of this kind of model for only 2 or 3 degrees of freedom have been studied in the literature. For example, the active Ornstein-Uhlenbeck particle model is a special case of this setup. And now we want to study this in a more general sense, and therefore we have added n degrees of freedom and specifically consider the non-reciprocity. And we, due to the linearity of this model, we can compute things like the heat dissipation and the entropy production rate analytically. So this is a good playground to understand the effect of non-reciprocity. So what we find is that in general, having non-reciprocal coupling brings the system out of equilibrium. The system can reach a non-equilibrium steady state where it has finite heat dissipation and a broken detailed balance, even in the absence of temperature gradients. So if all the temperatures are the same. And this is because we need to supply work to the system in order to sustain this non-reciprocal coupling. However, there's also special cases if we introduce a temperature gradient in the system. We can find the condition where the temperature gradient and the non-reciprocity somehow cancel each other, and the system reaches a steady state that looks like equilibrium, in the sense that it doesn't have any dissipation, there's no irreversibility, the entropy production rate is 0, and the system fulfills detailed balance, yet there's a temperature gradient in the system. So I found this personally quite interesting, because I have not seen before a system where multiple thermodynamic drives compensate each other in this way. So in this case, the temperature gradient and the non-reciprocity can compensate. If we increase the non-reciprocity even more, we can also find a state where, or a regime where we can introduce a heat flow from the cold to the hot side. So having non-reciprocal coupling yields a refrigerating effect on the cool bath. We extract energy from the cold side and release it on the hot side, different from the usual direction of heat flow that you usually have in reciprocal systems. And to avoid confusion with the sign of the heat, so here I'm really talking about where the energy is extracted and where it's going to. So taking everything together, on average, the system, of course, still obeys the second law of thermodynamics. And another thing I want to mention is, if the off-diagonal elements of the coupling matrix have different signs, the dynamics also becomes very interesting, because then one particle is attracted while the other particle is repelled. And this can induce a run and catch like scenario. We will hear a talk by Rosalba Garcia Milan about that, I think tomorrow. But here I want to stress that the reversed heat flow is not possible under these conditions, but it's only possible if both off-diagonal elements have the same sign. One can ask what happens if some of the degrees of freedom are not observable. This is a very valid question, because in many of the models that have been discussed in the literature, this is the case. So here some variables are just dummy variables, auxiliary variables, or they are unobservable. And then the dissipation of these variables is questionable. So what we can do instead is we can derive a generalized second law in this case. So then the heat dissipation is not bounded from below by 0, but in this case, it will be bounded by the information flow. And this is a well-known result from the field of information thermodynamics. And here we basically just embedded this system in this scheme. But we also generalize this to arbitrary particle numbers or numbers of degrees of freedom. I should say that this is the definition of the information flow, and this is connected to the mutual information, the time derivative of the mutual information of the 2 or n degrees of freedom. And I think the take-home message for those who are not familiar with this framework of information thermodynamics is just that, if you have a more complicated system and you coarse-grain some degrees of freedom, you will need to take into account information flows to connect the entropy and the dissipation. And the connection between entropy and dissipation is not the usual simple one anymore. Now in a recent project, we have realized this non-reciprocal toy model in MD simulations in order to study a little bit whether some of the results might depend on the framework that we use or not. In MD simulations, the notion of, or the way the heat is calculated is different. It doesn't stem from the particle dynamics, but it stems from the bath particles. There's a thermostat acting on the bath particles, and it resets the particle velocities in the bath, and therefore by this resetting we can extract the heat flow. So there's a different way of measuring the heat, and what we found is that we have a good agreement between our theoretical predictions and the MD simulation results. And that is not only true for the averages, but also for the fluctuations. So for example, we can calculate analytically the power distribution, and it matches very well with the MD simulations. And we can also see that the thermodynamic uncertainty relation provides a good bound here for the uncertainty of the work, as we have expected. And we also studied the system from the perspective of a refrigerator. So we consider this as a nano refrigerator. And then it makes sense to consider the efficiency, in this case, given by the coefficient of performance of the refrigerator, which is given by the heat extracted from the cold bath divided by the total work that must be applied in order to sustain the non-reciprocal coupling. And what we found is that the average efficiency is given by a quite simple expression that is in particular independent of the temperatures. And the fluctuations of this efficiency obey a power law with the exponent of -2, and this matches previous theoretical predictions from the literature. And here we see that this also holds in the MD setup. Yeah, I have said in the beginning that another kind of non-conservative interactions are time-delayed interactions. In this talk, I do not have the time to really discuss this topic, but I just wanted to give some of the main insights. But I've seen that some of the biggest experts on this topic are in the audience. So if somebody is interested, I encourage you to take advantage of that and maybe ask me and the others more questions in the discussion if you're interested. So, of course, if we have time delay in our model, the description becomes way more complicated. First of all, we have a non-Markovian process. Second, this Langevin equation with some time delay is an infinite dimensional stochastic equation, which is really annoying to handle mathematically. And I just want to here give you some a glimpse on the problems that one encounters. So for example, if we want to calculate the entry production rate in the way that we know for Markovian systems without time delay, and that means we consider the path probability of a forward trajectory divided by the path probability of the time reverse picture of that trajectory in the time reverse process, then we will find that in this case, the time reverse process becomes a very peculiar object. And this is because if you reverse a history dependency in time, you end up with an acausal dynamics, which depends on its own future. And I think this shows us that having any kind of delay or memory introduces a different kind of error of time. Of course, we can only memorize our past and not our future. And if one carries out the math, then you find that in addition to the medium entry production and the system entropy change, there is again an information theoretical contribution, which is a quite complicated path integral in this case. And however, to give you again something intuitive to think about, you can again consider the heat flow, and what we could show for linear systems, and which has also been shown in other references, is that having such a time delayed force can also introduce a reversed heat flow. So if you have a particle in a fluid and you steer it from outside with a force that is proportional to the delayed particle position, then even for very small time delays, you can find conditions where you will actually cool down the fluid by doing so. So this is very different from a usual drive where you would, by steering a particle, always heat the environment. If you steer it with this feedback force, you can cool down the environment. And this is in effect known from the field of feedback cooling. And the reason is, or one way of understanding is that you cannot have such a drive for free, but you have to measure something about the system first. So in a sense, you always have some sort of controller and some sort of intelligence that acts here. And if you would take that into account, you would also, again, of course, see where the entropy is going to. Or you can also consider this effect from the perspective of entropy pumping. Having a delay force is similar to having a velocity-dependent force. So I want to spend just 1 more minute giving you an outlook of what I'm working on also right now. Is many-body systems with non-reciprocal interactions. So I'm interested in the question, what happens to the global behavior of a system if I have non-reciprocal coupling? And in this case, we consider an XY model in 2 dimensions with nearest neighbor coupling. But we modify it in a way that each spin now only interacts with the spins that lie in the finite vision cone in front of its current orientation. And what we find by performing Monte Carlo simulations on the system is that in addition to the disordered and quasi-long range ordered phase, we find a long range ordered phase, which usually doesn't occur in 2 dimensions in the XY model. So the non-reciprocity here can introduce long range order. And this is a very interesting result because it may be a hint why natural systems can form so well order. And what we see here is that non-reciprocity is definitely one of the mechanisms that can help the system to order. And this is even true for very big vision cones, so even almost 360 degrees. And if we look at the spin dynamics, we also
Sarah,
see...
you're entering your discussion time.
Yes, perfect. This is my last slide. Thank you. Yeah, so also when we look at the spin dynamics, we see quite interesting behavior if we have these non-reciprocal coupling. So here we consider an ordered system, and we introduce 2 defect lines at time 0 by rotating the spins within 1 band. And then when we start the simulations, we see that this band will travel in a preferred direction, which is, of course, very different from an equilibrium system where defects would always diffuse in all spatial directions. And this introduces also, of course, irreversibility. If I would play this video backwards, the stripes would wander in the wrong direction. And this can be measured by the entropy production rate. And we find that the entropy production rate has a maximum in the disordered phase. So the defects that are in the system travel in a directed manner, and this seems to be the strongest here, close to the phase transition in the disordered phase. And with this, I want to close. I want to thank you first for your attention, and let me just remind you that I have discussed 2 classes of non-conservative interactions. I hope I could convince you that they are important. They can introduce reverse heat flow from cold to hot. I also showed you these pseudo-equilibrium states, and at the end gave you a glimpse on impact of long-range many-body systems. In this paper that I'm referencing here, we also discussed a many-body system with delayed interaction, and also found that having an intermediate delay can enhance the stability of a swarm. So yeah, with this, I want to close and thank you all for your attention.